All right, welcome back to more physical chemistry. All right, this is topic 2C, thermochemistry. I'm going to fly through this and go straight to 2D also, right? Because thermochemistry is exactly as you remember it, basically, right? In thermochemistry, we use values for several standard enthalpies, like this H naught, right? The standard states, and this is going to be pure form at 1 bar, right? It's approximately 1 atmosphere, which is what we use in general chemistry. Technically, it's 10 to the fifth, 100,000 pascals, but close enough. All right. Our standard enthalpies are generally understood to be at 298 Kelvin, unless otherwise noted. Like this is the example where it's noted at a non-standard temperature, right? H naught at 373 Kelvin would be 40 kilojoules for whatever this particular thing is. Right. Now we've seen this before, right? Our H, we have enthalpies of reactions and transitions for many, many different things, right? Uh, in Gen Chem, we used fusion and vaporization, sublimation, right? We use H of the reaction. Often we did like Rx in for reaction instead of just R, but it's the same difference. Heat of combustion, heat of formation, we used all of those, right? So we just have little subscripts to denote um, specific reactions or transitions. That's all the subscript means. Again, we've seen that before, right? And ideally, since H is a state function, right, the enthalpy of two kind of conjoining uh, reactions should add up to the total reaction, right? So fusion is going from solid to liquid, and vaporization is going from liquid to gas. Then the enthalpy going from solid to gas, sublimation should be equal to the enthalpy of fusion plus vaporization, right? Because this, again, H is a state function. So it doesn't matter how we get there, it just matters where we start and where we end. Should add up together, right? And since it's the state function, right, if we have a reaction going from A to B, right, it should be the same magnitude, but the opposite sign of the reverse reaction going from B to A, right? Same magnitude, different sign, either positive or negative. Nothing super new here. Right? Right. Sometimes we use the standard enthalpy of formation, right, which is indexed against the reference states of the elements in their most stable state at a specified temperature at 1 bar, basically 298 Kelvin, 1 bar. Right? If we think of a reaction being reactant atoms disassembling and reassembling into products, right, then the total enthalpy change is going to be, right, enthalpy of a reaction is going to be the sum of all the products, right, the heats of formation, the sum of all the heats of formation of our product, right, minus the sum of all the heats of formation of our reactants, right? This is exactly what we did in Gen Chem, right? There's just extra, it just looks like extra fancy notation right here, right? This is the number of moles of each product, right? And same thing over here, right? Number of moles of each reactant, right? Same thing, exact same thing that we did in Gen Chem, which is why I'm not gonna like cover it too much because this is absolutely not new information, right? Just products minus reactants. Done that before. Oop, go back, right? Now, one thing we do need to remember is that our temperature changes enthalpy, right? We talked about that, right? That's the whole point of our CP, right? It was the change in enthalpy as the temperature changes at constant pressure, right? We know that enthalpy changes with temperature, right? If we can't look up the enthalpy at a specific temperature, we can calculate it, right? So the enthalpy change for a single substance is going to be, right, the new enthalpy at the new temperature equaling the original enthalpy at the first temperature plus Cp times delta T, right? Cp times delta T, right? Because if Cp is H over T, right? If we multiply by delta T or dt, same difference, right? We get H, right? It makes perfect sense, right? I mean, you can almost think of this as like this is almost like y equals b plus mx, right? That's kind of what we're looking at here, right? And this is going to assume a little bit that Cp is constant over that temperature change, right? That's going to be sort of the whole idea of it, and it's going to be constant. All right, if it's not going to be constant, then we're going to have to make things more complicated, but we're not going to do that. We're going to keep it pretty easy. All right, and if we wanted to look at an entire reaction of substances, all right, we could do this for an entire reaction of substances, right? We could have delta H of the reaction at one temperature equals delta H of the reaction at the first temperature, right? Plus the change in temperature, right? T2 minus T1 is just the change in temperature times the Cp values of the reactants, right? So this is Cp of the, sorry, not the reactants, the Cp value of the entire reaction, right? Cp value of an entire reaction. If we wanted to look at that, right, the C of an entire reaction is still going to be exactly the same as delta H, basically, right? We just take C of all the products times, again, the number of moles, right? Because we're assuming this C, if this is Cp, is not molar, right? If it's not molar, then we need to include the number of moles here. Right? If it was like CPM, then we could just add all the products and all the reactants and go from there, right? But anyways, C of all the products minus C of all the reactants to get C of our reaction. So the exact same thing we did with H. All right. Where'd it go? Boop, boop. I put it going too far back. Right, the exact same thing we did with H. Right, exact same thing, just now using our CP values. Right? No difference. So it's the exact same math. It's super duper easy as long as you're given the numbers, right? And one thing you will notice is that well, you know, this, I'm not going to do any questions about this particular one because, like I said, it's literally stuff we did in Gen Chem 1. Like, there's no difference. The only difference here is that now we do this, but this is the exact same thing as old Hess's law. So it doesn't make any, you know, there's no new skills here. You just have to have the numbers and plug them in and go. So I'm not going to be doing an example of that. No big need for that, I should say. So let's skip on to, oh, we forgot about this part. One little thing I want to talk about here was about differential scanning calorimetry. Right? Now, eventually, when we get into the new building, we're going to have a DSC, right? And this is going to be able to do lots of cool things for us, right? But a DSC here is measuring the change basically in CP, right? Versus an external reference. Here's the external reference, right? And basically what we're measuring is the amount of heat required to raise the temperature, right? The amount of heat required to raise the temperature, right? And as the CP changes, right, then the amount of heat needed to raise the temperature also changes, right? That's what we're looking for here. And so what we see here in this particular one, right, we see a positive value CP, right, which is going to indicate an endothermic change here, right? We have to add more heat that's endothermic, right? Excuse me. Have to add more heat, which is endothermic. And then, right, if we wanted to get the actual delta H of this particular change, in this case, it's some sort of conformational change, right? Then it would be the integration of this curve, right? This curve is Cp, right, x times dt, basically, right? So it would be the integration of this curve would get you delta H for this particular conformational change here, right? For this conformational change. So differential scanning calorimetry actually very, very useful because you can look at lots and lots of different changes, anything that has a delta H that, we can measure, we can look at that basically. It's not going to be super useful for things like combustion, right? Because it's not a sealed little container here. But it's really, really useful for looking at conformational changes, going from solid to liquid, like vapor, fusion, other things like that, where there's not huge volume changes, to put it that way. It makes it very, very easy. Now, let's get into section 2D, which is more new stuff. Okay. State functions and exact differentials. So previously we talked about how U change with changing temperature, right? We talked about our CV was our U over temperature at constant volume, right? That was CV. All right, we can do something similar for any pair of variables like P and V or V and T or P and T, right? We can do the same different things, the change in internal energy with regards to two different variables changing and one staying the same. All right, if we start with V and T, all right, this is going to get us the simplest expressions. Again, this is not that simple, but it's the simplest expressions. Right here, we'd have du, all right, is going to be du, squiggly du over dv at constant temperature times dv, right? And then du over dt at constant volume times dt, right? The partial derivatives kind of added together. Right, now, if we look at the right-hand side, right, this is exactly what it's rearranged version of what we wrote up here, right? du over dt constant volume is CV, right? But this new version over here, which is du over dv at constant temperature, this is going to be our new value that we're going to call internal pressure. I'm trying to make my V's and U's more distinct. Sometimes it's hard. I go really fast, right? But this new thing is going to be internal pressure, right? So this internal pressure has the symbol pi sub t, excuse me, pi sub t. This is the change in internal energy as the volume changes at constant t, right? So pi sub t, that's the change in U, the change in V at constant temperature. Right? So the change in energy occurs as the level of intermolecular interactions change while a gas is expanding or contracting, right? So it's all about the intermolecular interactions here. Now, in a perfect gas, there's no intermolecular interactions, so the internal pressure would be zero. There would be no change, right? But in real gases, we're going to have a lot of difference, right? So for instance, as we compress something together, right? As we compress it together, right, closer and closer and closer, eventually the repulsions are going to be dominant, right? And as our volume gets smaller, our internal energy is also going to get smaller. It's going to what's the word? It's also going to change, right? But if it's attractive, if there's attractions that are dominant, then as we push them together, right, everything is going to be attracted more. And so the internal energy is going to change, right? If attractions are dominant in real gas, internal energy increases with volume, right? Because the molecules become farther apart on average, right? Again, if they're attracted to each other, when they're close to each other, that's more stable. So there's lower internal energy, right? If repulsions are dominant, the internal energy decreases as the gas expands, right? If they're repulsed from each other, then when they get farther away, there's less, the more stable version is them being far away, right? This is our internal pressure, right? du over dv at constant temperature. Right. Now, if we rewrote our first equation, meaning this one here, right, we fill in now the symbol for internal pressure. Right, what do we get? Now our du is equal to internal pressure times dv plus our constant volume heat capacity times dt. Right, now we have a little bit nicer version of our particular, excuse me, equation here. Right? If we do the same thing, right, we can apply it to the other V's and P's. And, if you look at this, we've done V and T, right? Well, we can do P and T, we can do P and V. We can do both of these things, right? Let's do the little bits, right? So if we see how U changes at constant pressure as a function of V and T, right? du at constant pressure, which is different, right? This is different than what we had before a little bit, right? Because this was, right, this is constant temperature, this is constant volume, right? We're going to do a different variation. When you have three different variables, there's lots of different variations here. All right, we're going to take our previous equation, right? Equation equals internal pressure, dV plus CV dt, right? And we're going to divide everything by dt, right? So that cancels out. This is divided by dt. This is divided by dt. And we impose constant pressure, which is what the little brackets down here mean, right? Then we can find like a little bit of a new form, right? So the right-hand partial derivative, this derivative of this with regard to dt, right, it's going to be defined as a new property. This is the expansion coefficient alpha. Right, it's physically the change in volume as the temperature rises. Right, so our alpha is going to be 1 over V, right, 1 over V times delta V over dt, whatever. Right, V over T, right, dV over dt at constant pressure. Right. We can also have a similar function, right, which is our isothermal compressibility. This isothermal compressibility is going to be slightly different. Negative 1 over V is, oops, my bad, times dV over dP at constant temperature, right? Very, very slightly different, which is what makes it annoying, right? Which is the change in volume as the pressure changes. Right? This is the isothermal compressibility. Now, if we introduce the expansion coefficient, right, into our du dt equation, right? So this expansion coefficient, 1 over V times dV over dt, constant pressure, right? Well, if we put that in for this, basically, right, dV over dt, constant pressure, we include that in, right? We have to include the 1 over V too, right? Then we would get d over dt at constant pressure being, right, we have the internal pressure, right? We have the expansion coefficient. And then we also are going to have still plain old CV. All right, still plain old CV. Right, so now we have a nice looking equation here. Right, it's going to make everything a little bit easier. Right? Right. This equation is entirely general, provided the system is closed and the composition is constant. Right? And it expresses our change in internal energy with regards to temperature. And if we have three different variables, or not three different variables, three different constants, right? Which is very, very nice. We're actually four different constants, right? Internal energy pressure constant, expansion coefficient is a constant, right? Volume is a constant, heat capacity is a constant, right? So it works out fairly good. And then if we wanted to, we could relate CP and CV. This is a little bonus one. Don't think I have it. Yeah, I don't have it yet. We can relate CP and CV. If we were to do that, we would get, right, this isothermal compressibility in here. That's where we would pop in. But honestly, we're not going to be worried about this too much. Right, again, this is just extra. I'm not worried about it too much. Right. All right, one thing you will notice is that for this particular section, there's not any questions about this on the problem sets. That's honestly because it was just hard to find real good questions involving this stuff that just didn't go into like rabbit holes that I didn't really want to go down. So we're just going to learn it and then kind of mostly forget about it, to be honest. Right? Now, if we want to do the same thing with H instead of U, right? We know that definition of enthalpy is U plus PV. Right? Same set of things. We're going to do focus on change in pressure and temperature. Right? If we do so, we get the new value of the Joule-Thomson coefficient. This is mu, right? This is dt over dp at constant enthalpy. Okay. And eventually this will feed into an overall equation here that our dH is equal to minus mu times Cp dp, right? Plus Cp dt, right? Very, very complicated, right? And this is the variation of enthalpy with pressure and temperature. Right? So let me scoot back a little bit. So we are looking at dH and variation of enthalpy with pressure, right, at constant temperature, right, and the variation of enthalpy, whoops, that's an H, with regards to temperature at constant pressure, right, this is where we're looking for, excuse me, right. Well, if we look at this, delta H, or sorry, dH over dt at constant pressure is Cp, right? That's what the definition of Cp, right? The change in enthalpy as the temperature changes at constant pressure, right? And then for dH over dP, this is what we just defined as the Joule-Thomson coefficient, right? This is what we define as a Joule-Thomson coefficient here, right? Same sort of difference, right? And so this is how we get in here, right? This is where our Joule-Thomson coefficient comes in, right? It's a little bit more of, how do I say this? A lot of rearrangement from here to get down to here, but this is sort of the summary version of it, right? The variation of enthalpy with temperature and pressure, right? And luckily, again, we got basically a lot of constants, right? This Joule-Thomson coefficient, basically a constant. Cp is a constant, and that's basically everything we need there, right? But that's mostly it for this particular section. This particular section, 2D, not my most favorite. Again, very hard to find good questions about it, but figure we go through it and touch on it a little bit. Let's see. Yeah, and we'll stop there. We'll pick up 2E in just a second.